Good afternoon, everybody. Um, my name is Adeu Sibolo Atfe, and I'm staff of EdSofta. So we at EdSofta here. Good afternoon, everybody. We are so sorry about that. Okay, so we at EdSofta here. I'm decided to create some sort of tutorial to help JAMB students their final stretch for the final preparation of their exams. Yeah, okay. So today we're going to just be treating physics, just topics from physics. And before we get into that, I just want to quickly, so what or who is or what is EdSofta? So EdSofta is a tech company. Yeah, EdSofta is a tech company that what we do here basically is we we're a tech company actually. So we create apps that help students to prepare for exams. So we just create solutions to help people, to help students prepare for various type of exams. So what we have on the market right now is EdSofta UTME and EdSofta SSC. So obviously we're going to be using UTME for our session today. Okay, so as usual, this tutorial is powered by EdSofta. Let me just make this full screen, okay? So this tutorial is powered by EdSofta, and EdSofta is an app. EdSofta UTME actually is an app that prepares students for JAMB UTME. It has past questions, study materials, and many other features that help students prepare for the exams. Yeah, so it is a solution. It familiarizes you with system. Then we have a lot of cool features packed for you in the app. Okay, so for this tutorial, we will be solving questions from the EdSofta app. Yeah, the desktop app to be precise. Yeah, and then if you want to have the EdSofta app, so we have the Android version and we have the desktop version. So majorly running on Windows. So if you want to download it on your Android phone, just simply go to Play Store and search for EdSofta UTME. Just search for this, and then you would be good to go and install it. And then obviously to have access to all its features, it's not totally free. To have access to all its features, you would need to activate the app. Yeah. Okay. And if you want to have it on your desktop also, it's pretty simple. Just go to www.edsofta.com and click on downloads. And then you'll see a list of all our products that we are products. Click on products, you'll see a list of all products that we have, and then you can download for the desktop. Okay, so first of all, we'll walk you through the slide. So basically what we're talking about now is we're talking about electricity, current electricity. So I'll take you through the slide. Then once we are done, then we'll solve questions from the EdSofta app. Yeah, we'll solve questions from the EdSofta app, and then after that, then we'll take questions from you. Okay. Yes, electricity. So actually there are two types of electricity before we go on. There's static electricity and then there's current electricity, right? Okay, so static electricity is just so it's so this type of so how you generate this type of electricity is just pretty simple. I don't know if you've done this experiment when you were in SS1 or so, because I remember that I did that when I was in school then, where you would rub the cover of your pen on your hair. So that's assuming your hair, you don't rub any hair cream or any lubricant. So your hair is very dry. So you are rubbing the cover of your pen, which is meant to be plastic, vigorously. on your head, and then by the time you put it near small pieces of paper, that it attracts those small pieces of paper. That is just static electricity. Um, that's just static electricity. There's nothing much that you can do with static electricity. Current electricity is actually what powers most of what we have. So there are different types. You have the alternating current and you have the direct current. So current electricity is like the main thing that we are used to. So let's just go basically go through some definitions real quick. So electricity is the flow of charges. Simple. The flow of charges, as is simple as that. Electric field generally refers to, sorry, before I move on, charges. What we mean by charges here are just electrons. We go back to the fundamentals of physics. We have protons, we have neutrons, we have electrons, and then so those electrons carry what charges. So that's just basically, so guys, some textbook will tell you the flow of electrons, so flow of charges, positive or negative. Yeah. So electric field generally refers to the space around an electric charge within which any other charged body experiences an electric force. Okay, so I think it's self-explanatory itself. So take this for example, this is an electric charge. So as far as I can influence, so this is an electric charge. So as far as I can influence within this circle, yeah, let's just this imaginary circle, I can influence any other charged body in this circle. This circle is what? An electric field. So that's just it. So it's just the space in which an electric charge can influence another electric charge. So that's just it. So if this is my charge, so within this boundary, within this circumference, it can influence these charges. So this whole circle is called what? An electric field. So it could be big, it could be small, depending on how strong the charge is. Okay. So resistance is the opposition to the flow of current. Yeah. Self-explanatory also, because we don't want to like bog everybody down with a lot of very high level definition. So just simply resistance is the opposition to the flow of current. I've had this definition with me since SS1. So when somebody asks me what resistance is, it's just the opposition to the flow of current. So you're not totally preventing, because that's what an insulator does. Do you understand? So that's what I'm preventing, an insulator and a insulating material and a resistor, because a resistor that does anything that offers resistance is called a resistor. So what it's just doing is it is opposing the flow of current. So it's somewhat reducing it, just reducing. So it's not totally cutting it off. So that would be what an insulator. So insulation is just cutting off. So you are preventing the flow of electricity. You are preventing the flow of current. So current is not flowing. So that's what insulation is. But resistance is just merely just, for example, let's look at this example. There's a tap, right? So when you open the tap, I don't know if you did this when you were a kid, where you would try to use your hand to block the tap, and then no matter, some people would, but depending on how like the force with which the water is coming out, sometimes you try to use your palm, but you see that the water still spills out. So that's kind of a picture that you could paint with resistance. So you're not totally cutting water off, you're just restricting how much water gets to the bucket or something. So that's just for resistance. But when you just put maybe you put something that can fit into the tap's mouth and you just apply enough force and you block the tap, so that's insulation. So you are preventing water from even coming out at all. Okay, so current. Yeah, current is the rate of flow of electrons. So how quickly can electrons flow? How quickly can electrons move? How quickly can they move? So that's just current. So current is just a measurement of how quickly I can move electrons from point A to point B. Okay, then voltage is the difference in potential difference between 2 points. So so the idea here is this. So voltage is just simply simply the potential, the difference. So 2 points have a particular what's potential difference, right? Okay. So now the difference, because what happens is that current tends to flow from a point that has a higher potential difference to one that has a low potential difference. So now the rate at which it flows, the difference, so it could be the difference between the two potential differences could be big or it could be small. So that difference is now what we refer to as voltage. Okay. So now, then what is potential difference actually? Because we just mentioned here that voltage is what the difference in potential difference between 2 points. So to avoid some kind of tautology, I'm not going to say voltage is the difference in PD. So that's short for potential difference, right? So in PD, the difference in PD between 2 points. So now, what is potential difference, or in short, for short, PD? So potential difference now is the amount of work done, right, in moving a unit positive charge from a point to another, mostly from a point of lower to a point of higher. So potential difference is just what the work done in moving one. So it's just like, so potential difference, for example, so in a battery now, so a battery has a particular potential difference, right? So the potential difference of that battery is just the amount of work it has to do to move one electron from one point to another. That's just potential difference. So voltage is now saying, okay, I now have what, 2 batteries, right? Which each with their own what potential differences. Okay, so now I will now want to know the work, how much work I need to do, because that's what voltage actually is. How much work I need to do to now move current or to move electrons from this battery with a particular potential difference to this battery with another particular what potential difference. So that's just what voltage for you. Okay, so and then we have it's measured in volts, and what we have here is what W is equals to what QV. That's potential difference for you. W is equal to QV. So where W is what work done, then the Q is quantity of charge, and V is potential difference. So W here is work done. So V, if you wanted to calculate for V, right, what you would have is, or you make what V is of the formula. So V will now be, so you now have V, which is potential difference, to be equal to V will now be equal to W over Q. Yeah, V will now be equal to what? W over Q. So if you calculate a potential difference, you just need to do that work done over quantity of charge. So the work done here is now like the total work done in moving everything. So potential difference is just total work done. So it's just proportion. Do you understand? So potential difference is the energy required or the work done to move one, right? So now if you now know, so if, for example, it takes battery has potential difference of 5. That means it takes 5 joules, right, or 5 volts to move one charge from one point to another. So let's now assume I now have 20 charges, right? So that means the total work done will be what? 5 times 20. So that's total. So that's why I said this work done is what the total work done. Or this potential difference is just work done for the smallest. That's why they use the word unit. So for the smallest possible charge. Okay, so now there's a very important law in electricity called Ohm's law, right? Okay, so Ohm's law, very straightforward something. Ohm's law states that the electric current in a given metallic conductor is directly proportional to the potential difference applied between its ends, provided that the temperature remains constant. Okay, so what that simply just means is, let me just keep this slide somewhere, and sorry, let me just bring up my board. Okay, I got my board. Sorry, let me just get rid of all of this. This was like a result of what we did at the last lecture. Okay, so what it just says is that let me say what it means again. So Ohm's law states that the electric current, in a given metallic conductor is directly proportional to the potential difference applied between its ends. And remember, voltage is what? Voltage is the difference between potential differences in 2 points. Do you understand? So what it is directly saying here is that the current, which you take as I, is directly proportional to the voltage. Okay, that's it. So it goes the other way. You can either have it like this, or you can have it like this. V is directly proportional to I. And then remember, from mathematics, when you want to remove the sign of proportionality, what you just do is, so this is equivalent to introduce a constant, right? You can have what? I equals to what? KV, or I can have V equals to KI. Okay, so this is the preferred method of writing it. This is what you see most of the textbook. V equals to what? KI. But now, these are constants here, right? These are constants. This are constant now is now assigned to be the what? The resistance. So K now is supposed to be what? Our resistance. So if K is our resistance, then we have a new formula, which is what? V is equals to what? I R. So this is where that formula comes from. Formula is derived from what? From Ohm's law. The formula is derived from Ohm's law. Simple as that. And this formula is very fundamental in a lot of things that we would solve in current electricity. It's fundamental to a lot of things that we would solve in current electricity. So let's go back to our slide. Okay, sorry. Let's go back to our slide. Okay, so that goes to explain Ohm's law. That's just Ohm's law for you. So, and then the caveat here, the restriction here is that provided that the temperature of the conductor and other physical quantities or physical factors remain constant. So, what Ohm's is saying here is, in an ideal environment where you can control temperature, air resistance, and all the other physical factors, in an ideal environment where these things can be controlled, the electric current would always be directly proportional to what? To the potential difference applied between its end. Okay, so now key points. So just some things to note. Yeah, cells can be arranged in series of parallels. So cells are like batteries, right? So cells are like batteries. So batteries are a group of cells. So cell is just what? An individual, just cell is like smallest form of something that can give you what electricity, that can give you current. So that's what a cell is. So cells can be arranged in what? In series or in parallel. So now when they arrange in series and in parallel, so you can have a circuit, right? You have a circuit that has a resistance, that has a cell. You can have a circuit that has a voltmeter. The point of having a voltmeter so that you can measure your voltage. So you can have a cell, you can have a resistor, yeah, and then you might have something you might have something in there also that measures your current so that you can track what's going on there. But now, so all I want to note here is now we can arrange our resistors in two ways. Actually, we can arrange them in what? In series and in parallel. So quickly, let me just show you guys what that would look like, right? So what does it mean to arrange it in series or, or in parallel? It's actually pretty straightforward. Okay, actually pretty straightforward. Okay, um, so when you have something like this, pardon my diagrams, I might not be the best. Actually, I don't even know how to draw. Okay, sorry, this is wrong. This is not how a battery looks like. Sorry, let me start from the beginning. Okay, so now I have a cell. So this is what a cell looks like. So it is connected and then connected to resistor 2, connected to resistor 3. Then I can now have my voltmeter here to measure the amount of the voltage. Then, so this is a circuit, right? So now this is my resistor. So I have, this is R1, R2, and R3. So now, because they are connected to one another, they are connected in what? In series. So the resistors are connected in what? In series. So to now know the total resistance of the circuit, to understand total resistance of the circuit, is actually very straightforward. So you just simply add, so R total will be equal to R1 plus R2 plus R3. Simple. And that's your total resistance. That would just be your total within my words. Sorry. R total, that's how you calculate your resistance in what? In series. So when parallel, you have first of all, you even have a very different diagram. So let me just get rid of all of this. You have a very different diagram. Okay. So yeah, so this is what your this is what it will look like. Okay. Sorry. Sorry, let me. And then pardon the fact that I'm always drawing it in threes. You can have two, one, but just to like illustrate a point. It's just to prove what I'm trying to what see here. So I can Oh, wow, sorry about that. Okay, so let's just see ends here. So we just have that like that. We have it like that. So and I have something like this. Okay, so this is a representation of what A. So what we have here is we have this is R1, this is R2, this is R3. Now, what differentiates? So now this is an example of what of a parallel connection. And why do we say parallel? Sorry, why do we say parallel? We say parallel because the resistors are not connected together. Do you understand? They all are connected to the circuit with different wires, with like on different points. See now, this guy is connected to R1, which is further connected to R2, which is further connected to R3. But for parallel, it's like this is the connection, yeah. And then I take my part, so it branches off. This part branches off. Um, this part branches off. This part branches off. This part also what branches off. Do you understand? So they are not. If I had a connection here, right? If I had a connection here now, then like from here to here, then would be in what in series. But because the resistor is not connected, they are not connected to each other in any way. They are independent. So that's why we say that they are parallel. So now the question, which begs now the question, how do we now know the total resistance of the circuit? Okay, so total resistance of the circuit just becomes 1 over R1 plus, sorry. Skip something here. Actually, I meant to write it like this. 1 over RC is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So once you are done, right? So you find this. Once you added everything here, you now find the inverse, so that you now have something like this. You have something like this. RC is equal to something. So instead of having 1 over RT, so once you've added everything together, once you've done 1 over R1, 1 over R2, 1 over R3. So let me give an example. So let's say, for example, this is 2, this is 1, and this is 4. Right? So to calculate it, what I would have would be this 1 over 2 plus 1 over 1 plus 1 over 4. And my LCM here would be what? Be 4. And this would have been 4 in here, 4 in 1, sorry, 4 in 2 in 4, 2, 1 in 4, 4. So 2 in 4, 2, 2 times 1, 2, 1 in 4, 4, 4 times 1, 4, 4 in 4, 1, 1 times 1, 1. So what do I end up with? I end up with what? 2 plus 4, 6, plus 1, 7. So I end up with what? 7 over 4. Then, so my 1 over RC is equal to 7 over 4. So we flip it. And it's RC now becomes what? 4 over 7. And then it's measured in what? Ohms. So it's like a little, this is the same, but something like this. It's measured in ohms. So this is how you would calculate it in parallel. But in series, using the same example, in series, what you would have just done is 2 plus 1 plus 4. And that would have just given you 7 ohms straight away. 7 ohms straight away. So it goes to show you that when you connect in parallel, you have the more resistors you have, the less resistance you get. Do you understand? When in series, the more resistors you add, the more resistance what you get. Because see, if I only had this 1 over 2 would be more than it is more than having 1/2 and 1 together. Or so like the more you add resistors, the lesser, so your total resistance reduces. But for series, total resistance will always increase. Okay, so so another thing I need to talk about here is this. So now, looking at it, there's something that happens to your current. So something is happening to your current and your voltage. Something is happening to your current and your voltage. So let me just get rid of this example here. Let me just get rid of this example, this whole space here, so I can create enough space for what I'm about to write. Okay, now in series, yeah, when you connect in series, something is happening to your current and something is happening to your voltage. So now I want you to notice that in series, current remains constant. In series, current remains constant, but voltage, what happens? Voltage, what is it called? Voltage varies. Voltage varies. Why? Why does voltage vary? Now, the reason why voltage varies is because they are connected sequentially, right? So sorry, let me be sure that I'm not making let me be sure that I'm not making a mistake here. Oh, sorry, I'm coming. Let me be sure that I'm not making a mistake here, because this part actually is a very tricky part. Okay, yes, I'm correct. So voltage across resistors in series varies while current remains what? Current remains constant. And why is that? Because now they are connected in series, right? So now when you release current here, now because this wire is the same wire, do you understand? So the flow of the current across these wires is the same. The flow of current across this wire is the same. But voltage has to now do what? Difference, potential difference. So now this resistance, voltage and this resistance will be different. When current flows through here, and when it gets here also, it will be different. And when it gets here also, it will be different. Do you understand? It will be different. But for parallel, the reverse happens. In parallel, the reverse happens. So what actually happens is, so current varies and voltage remains constant. Voltage remains constant. Okay, current varies and voltage remains constant. And why is that? Now, if you look at this diagram, okay, now it branches off. The way the connection works, it branches off. So this is the normal wire that like has the flow of current. So now once you get here, you are joining wires together, right? You are joining wires together here, you are joining wires together here, you are joining wires together here, so that's how it would work. So you are like using a lot of wires here, you are joining wire at both ends. Okay, so now what happens is this: because the voltage, so because we are branching off, right? So voltage, so the voltage remains constant because we're just branching off. We're not directly, so the resistor is not directly blocking the flow of the voltage that is moving across this wire here. It's just branching off it. Do you understand? It is branching off it. But now, because we've added lots and lots of wires, the current now varies. So the current, once the current gets here, it will be different. When the current gets here, it will be different. When the current gets here, it will be different because of the way we have added extra wires here. Do you understand? So that's what happens when you connect resistors in series or in parallel. So always remember, in series the current remains constant, but the voltage varies. While in parallel, the current varies, yeah, but the voltage remains constant. The voltage remains constant. Okay, so let's go back to the slide. So the voltage always remains what? Constant in parallel connection. Okay. So yeah, sorry. Okay, so I've written everything the same way here. Okay, so resistance, so this is the formula for series, this is the formula for parallel. Okay, now it says EMF also works the same way. So the electromotive force across is the same thing too, in series and in parallel. So it works, the same formula works for the both of them. So if you calculate total electromotive force in series, what you have is in series it will be E1 plus E2 plus E3 all the way. But for parallel, it will be 1 over E1 plus 1 over E2, so on and so forth. And then we've talked about this. Voltage across resistors in series vary while current remains constant. But current across resistors in parallel vary while voltage remains constant. Okay. So now, another thing to note also is that the resistance of a conductor is directly proportional to the length of the conductor and it was proportional to the cross-sectional area of said conductor. Okay, so this has to do with, so this is just resistance. So they are saying, okay, and mind you, yes, I wanted to say this. So now, another thing also that differentiates resistance from insulation, so resistor from insulator is, how do I put this? So now, every element or every material that can conduct electricity offers some form of resistance. Do you understand? Every conductor, anything that can conduct electricity offers some form of what? Resistance. So apart from normal resistors, everything that can conduct electricity offers some form of resistance. Your battery offers some form of resistance. That's why you see when we have something as internal resistance and external resistance. Hopefully, we would get to that in a bit. So that's when you have something like internal resistance and external resistance. So now, but an insulator does not allow current to pass through. Do you understand? So that's another thing to note. So the fact that you can conduct also means that you offer some form of resistance, and it could be a lot, and it could be a lot of factors, some mixture, when you have mixtures together, when you mix things together, some parts, some conduct, some don't conduct, and then based on an atomic level also, there's some form of what? Resistance. Okay, so we're now saying that, okay, the resistance of a conductor, so the resistance of how much a conductor would resist electric current is proportional to the length. It's proportional to length. So what that means is that the longer the conductor, the more the resistance. The longer the conductor, the more the resistance. The longer the conductor, the more the resistance. And it makes a whole lot of sense. So it's just like saying, let me just quickly go back to my board, and it makes a whole lot of sense. This diagram would make a lot of sense right now. Okay, so now imagine if this is a wire, right? And this wire offers some form of what? Internal resistance. So at some point is what? Internal resistance. Internal resistance. Internal resistance. So now, current flowing, sorry, something going to my eye. Current flowing, yeah, into this conductor. Now, if the conductor was just this length, so the total resistance, internal resistance here is not really much. Do you understand? But now, the longer it gets, that means you're having clusters of what? Internal resistance, clusters of what? Internal resistance, clusters of what? Internal resistance, on and on and on and on. So this would what? And this all they are what? Doing their fair share of what? Impeding the flow of current, impeding the flow of current, impeding the flow of current. So that means a longer wire will offer more resistance than a what? Than a shorter wire. Do you understand? A longer wire will offer what? More resistance than a shorter wire. But now, another thing to now note is that resistance also now varies inversely with the cross-sectional area of the conductor. So what that means is the bigger the surface area, the smaller the resistance. The smaller the surface area, the bigger the resistance. So what we now have is resistance is directly proportional to the length or inversely proportional to what? The area. So you have resistance is directly proportional to the length or inversely proportional to the what? To the area. Okay, so let me clear this part away. Okay, so having said that, I remember in mathematics, if you are to remove the sign of proportionality, what you have to introduce a constant. So what you have is what? R is equals to K L over what? Over A. So now our constant here now happens to be what? Resistivity, which happens to be like this. This happens to be the sign. So this happens to be the sign of resistivity. So that means we write this formula like this. It's called rho. It's a Greek alphabet. So you write it like this. Over A. Rho L all over what? A. So that's resistance for you. So this is another formula to keep at the back of your head. So it's going to come very handy in solving some questions. Okay, so now remember I mentioned something about internal resistance and external resistance, right? So now to calculate the EMF of a battery, right? The electromotive force of a battery. The reason was a battery is given as this, a current multiplied by what? The external resistance plus the internal resistance. So big R here is the what? External resistance. While small r is what? Internal resistance. Then obviously current here is what? I here is what? Current. So this is another formula also to keep in mind. It's another formula also to keep in mind. It will be very useful when you are solving questions in current electricity. Okay, so let's go back to the slide. Okay, so conductivity is the inverse of resistivity. Conductivity, is the inverse of resistivity. So the higher your resistance, the lower your conductivity. The higher your conductivity, lower your resistance. So that's just it. That's why they are the inverse of each other. Now, power is the rate at which energy is supplied or dissipated. Power is the rate at which energy is supplied or dissipated. And there are different formulas for what is it called? For power. You have power equals to current times voltage. You have, and power also. So the idea is this. This is how the formulas were derived. Okay, so work done. Yeah, work done in electricity. Let me just open up my board. Work done in electricity is given by this formula. Work done in electricity is given by this formula. Q equals to what? IV T. So this is what? I here is what? Current. This is voltage. And this is what? Time. So this is work done. So this is also another formula that we need to store. If we are told to calculate the work done, Q equals to what? IVT. So now power is now the rate at which work is done. So the word rate always means over time. Always means over time. So same as saying power is equals to what? Work done over time taken. So what we'll have here is what? IVT over what? T. So when T cancels out, you have P is equals to what? Sorry, let me make one here. P is equals to IV. So there are multiple formulas that we could use. So there's P equals to IV, there's P equals to V squared over R. Yes, there's also P equals to I squared R. So I know how did they get these formulas? They got these formulas by just manipulating these things. For example, V is equals to what? IR, right? If V is equals to IR, if I substitute IR here, what do I get? I get I times IR. So what that gives me is what? I squared R. Do you understand? But I also can, I is same as what? V over R. So if I substitute V over R here, I get to what? V squared over R. So it's just manipulation. So these two extensions that just came from substituting various formulas here. I hope you understand. And just to prove what I'm saying, so remember that V is equals to what? IR. Okay, so V, I made V is the formula. So if I substitute it in this place, I substitute it in this place, what I have is what? IR. Okay, and I times I is what? I squared R. Okay, so that's how they got this guy. Okay, and if I were to make I solve the formula here, I will have what? I equals to what? We divide both sides by R. I equals to V over what? R. I equals to V over R. So if I were to put this formula, we substitute it here. Okay, what I would have is what? V times V over R, which gives me what? V squared over R. So that's physics for you. We just have one formula and they'll just keep manipulating and manipulating that formula to like generate a lot of formulas. And what that does, it helps us because so that means somebody gives you the current and the resistance. Instead of having to first of all find the voltage, you can just quickly find the power. So having to find the voltage before you find the power, you can just quickly find the power directly using the what? Using the current and the resistance. Okay, so so back to our slide. Okay, so that's power for you. So now another thing that comes up in current electricity is electrolysis, and you might have seen it in chemistry. Yeah, it also happens in physics also. So Faraday, the as a constant is because actually it's one that founded electricity. Yeah, it's the one that did Mario Faraday was found out about electricity. So question now is sorry, I got lost in my train of thoughts here. So now Faraday now devised two laws for electrolysis. He devised two laws of electrolysis. So the first law states that the mass of a substance liberated during electrolysis. And wait, before I even dive into this, first of all, I think you should know what electrolysis is. Electrolysis simply is just using electricity to okay, so as a physician, sorry, as I say physician, physicist, sorry, as a physicist, right? Simply put, electricity is just conversion of what electrical energy to chemical energy. Do you understand? Now, to now further explain that, so what happens in electricity is you are using electricity to separate. Is a form of separate. Yeah, you're using to split or separate chemical compounds, right? So you see that in chemistry, there are some methods of preparing. There are some when you try and prepare some elements, maybe you're preparing sodium or something. You can prepare sodium through what electrolysis of salt. Do you understand? So when you pass salts, when you perform electrolysis of salt, you separate what sodium from what from chlorine. So do you understand? So that's what electrolysis just does. So when you want to extract, that's why. So it's just using electricity to um, to split or to separate chemical compounds. Okay, so now the first law of electricity states that the mass of substance liberated during electrolysis is directly proportional to the quantity of charge passing through it. It's directly proportional to the quantity of charge passing through it. Okay. So what it's just saying here is so quantity of charge here. So how do you know quantity of charge? Sorry, let me just quickly go back to our board. Um, okay, so let me just create space here. Okay, so now the mass is directly proportional to what the quantity of what of electricity, right? It's directly proportional to the quantity of electricity. Sorry, is proportional to the quantity of charge or quantity of electricity passing through it. So now M is directly proportional to so how we will write it is this: M is directly proportional to Q. And now the formula for Q, which is quantity of charge. Oh, I didn't mention. Oh, sorry, this is supposed to be. Sorry, pardon my mistake. This is supposed to be work done. This formula is supposed to be work done. Okay, not Q. So now Q, which is what the quantity of charge, is given by current times time. That's Q for a quantity of charge. Current times time. So we are saying that the mass is directly proportional to the current and what time. Let me try it in small letter. Time. Okay. So now, obviously, to remove personal proportionality, we add So sorry about that breaking connection. Yeah. Okay. So as I was saying, so last night I said was I was talking. We're talking about electrolysis. Yeah. Friday's first law states that the quantity, the mass deposited at the mass deposited at the mass deposited at the cathode or the anode, yeah, is directly proportional to the quantity of current passing through the electrolyte. Yes, it's directly proportional to the quantity of charge passing through the electrolyte. So now, second law of Faraday says that what? When the same quantity of electricity is passed through solutions of different electrolytes, sorry, this should have been electrolytes, the number of moles of the element deposited is proportional to the chemical equivalent with weight. So what we're just saying here is the ratio of the moles deposited is the ratio of the moles deposited is directly proportional to what the quantity of electricity passed through the electrolyte. Okay, so and with that we have come to the end of the slide. Okay, so quickly we'll just go through the app, yeah, and so that we can find some questions that we can practice with. Okay, so let me just quickly open up the EdSofta UTME app. The EdSofta UTME app. Okay, so okay, let me just show you from the beginning of how it looks like. So as you can see, it's a very has a very beautiful user interface. And so the thing we're actually concerned with is practice exam. Okay, so we don't want it to be a timer. We just want to practice questions. And then another wonderful thing that comes with EdSofta UTME is the ability to practice by topic. As you can see the text here, it says select subject, number of questions and topics of your choice to properly revise areas in a particular subject. Isn't that great? Instead of having to walk through past questions looking for a particular question or looking for particular topics that you look for particular topics that maybe you just read on that topic and then you want to practice questions on that topic instead of having to go through years and years searching for questions. You can just simply download the EdSofta UTME app right now, and you have that feature ready for you. So it's as simple as this. Select the subject you want, click on the select topics button, see a bunch of topics ready for at your choosing. So what we just did here was electricity, right? So I'm just going to scroll and look for electricity. Okay, find the electricity to be precise. Yeah, that's it. Okay, so select what? 10 questions. So let's just do 10. And then start test. Okay. So okay, so that we don't have the same problem that we had the last time. Share screen. Okay. So this is how our interface looks like. So now look at the first question. First question says a conductor has a diameter of 1 millimeter and a length of 2 meters. If the resistance of the material is 0.1 ohms, its resistivity is okay. So sorry, I'm going to be shuffling between using the board and using and then the question. So let's first highlight our parameters. So first of all, we have a diameter of what? Of 1 millimeter, right? you have a length of what? Of 2 meters, and then the resistance is what? 0.1 ohms, and we have to find what? The resistivity. Okay, no biggie. Let us open our board here. So let's just go to the board so that we can. Okay, so I'm just going to clear this whole thing so that we can have a new space to work with. And then I'm going to try as much as possible to manage my board, so the board, so that we can. Okay, so let me just split it right down the middle. Sorry, I know what. Let's just start. Okay, so if I recall earlier, okay, I have my diameter here is 1 millimeters. So let me just write that down. My diameter here is equal to what? 1 millimeters. Okay, and then I have a length of what? Of 2 meters. So this is same equivalent to 1 times 10 raised to power that should be minus 3 meters. Yeah, so that we can have it in the same unit. So milli is always 10 raised to power minus 3. So micro is 10 raised to power minus 6, and so on and so forth. So length is what? 2 meters. And then I was given my resistance as 0.1, if I'm not mistaken. I was given my resistance at what? 0.1. Yeah, that's correct. Okay, so I'm also to find what? My resistivity. Okay, so now remember, let me try it up here. We have what? Resistance is given as rho L over A. So now if I was to make rho the solid of the formula, I'll just simply cross multiply here, right? So if I cross multiply, what I have is what? RA equals to what? Rho L. Okay, so divide both sides by L, divide both sides by L cancels out. So what I'm left with is what? Rho equals to what? RA over L. So these are formula for what? Resistivity. Resistance times area over length. So first things first, we have our resistance, check. So we have resistance, check. We have length, check. What we don't have yet is area. Now, I noticed something, right? So the question gave us diameter. Now, based on that, I can draw a conclusion, yeah? Because I can only think of one two-dimensional shape, yeah, that has, because obviously we're doing cross-sectional area, one two-dimensional shape that has diameter as a property, and that happens to be what? Circle. Do you understand? So having said that, so if this is my diameter, so the formula for circle, if I think I can still remember that, is A is equal to what? Pi r squared. Oh, and then we have diameter. So I can convert this to my diameter and have that my radius r is equals to diameter divided by 2. And that gives me 1 divided by 2 gives me what? 0.5. So 0.5 times 10 raised to the power minus 3. Okay, so I have my radius, so that means I can continue. Okay, so now that I have that, so I can do this. 3.14, yeah, times 0.5 times 10 raised to the power minus 3 squared. Okay, which is something as 3.14 times. Now I don't even need to use what's it called? A calculator to know this. I know that 5 squared is 25, but now I have what? 0.5 here. Okay, I have 0.5 here. So now to make it easier on me, do you know that this 0.5 times 10 to the power minus 3, I can write it like this. And I write like this: 5 times 10 raised to the power minus 4. And how did I do that? Now, if I want to move this decimal place backwards, yes, if I want to move it backwards, I am what? I'm subtracting 1 from it. Do you understand? So even let me write this out. 0. So this thing 0.5 times 10 to the power minus 3 is same as so this is 0.5 times 10 to the power minus 3. 1, 2, 3. So this is 0.0005. So this is actually what I have. So now if I wanted to now do 5 times 10 to the power minus 4, what I have now done is what? 1, 2, 3, another level is 4. So that means I'm putting decimal point at the back instead of the front. So that means I have what? 5 times 10 to the power minus 4. So this makes it a whole lot easier. So you can write this as, sorry, I'll just write this as what? So I can write this as 5 times 10 to the power minus 4 all squared. Okay, so I know 5 squared is what? 25. So this is the trick. So when you want to do, so let me show you something. 10 raised to the power 2 squared is what? It means, sorry, 100, not the 10 raised to the power 2. Okay, so according to indices, yeah, even, yes, let's do 10 raised to the power 2. According to indices, yeah, according to indices, so this is 10 raised to the power 2. According to indices, what you do is what? You multiply the powers outside with what's inside. So what I end up having is what? 10 raised to the power 4. So using that same logic here, what I'll have is what? 25 times 10 raised to the power minus what? 4 times 2, 8. I hope that's clear. Okay, so now this is the tricky part. I have to multiply this whole thing together. So using a calculator. So if you notice, the calculator you have in JAMB does not really have decimal. Okay, does not really have decimal. So if you were to do this, but just for the case sake of this lecture, I'm just going to use the calculator to compute 3.14 times 10 raised to power minus 8. So I'm just going to bring up the calculator right now. Okay, so 3.14 times 25. Okay, so that just gives me 78.5. So what I have is 78.5 times 10 raised to power minus 8. Okay, so now I have my area as what? 78.5 times 10 raised to power minus 8. Okay. So now we can now what? Solve it. So I have what? Rho equals to what? RA. So my resistance here is what? 0.1. My area is what? Times 78.5 times 10 raised to power minus 8. So now I can write this my 0.1 as what? I can write it as 1 times 10 raised to power minus 1. So that it makes things a whole lot easier. So I'm just going to have 1. Okay. All over what? Okay. So if I multiply this whole thing, what I get is what? 78.5 times 10 raised to power minus 9 all over what? 2. And how did I get this? 1 times 78.5 is 78.5. Then now I'm multiplying this 10 raised to power minus 1 and this 10 raised to power minus 8 together. And using following the law of indices, says we have something like this. So my A here is -1 and my B here is -8. So 8. That's how I got to this. I'm going to divide this. So 2 in 7 is going to give us what? 3. 3 remainder. 2 in 7 is going to give us 3. It's going to give us 3 remainder. Sorry, it's going to give us 3 remainder 1. Yeah, 3 remainder 1. Sorry, I was checking something. That's why it took me a while to get that. So 3 remainder what? 1. Then 3 in 18 is what? 9. So you have your answer. So yeah, so 3.95 times 10 raised to power what? Minus 8. Okay, so let's go check our answer. Now, this took a long while to get this, yeah, but ideally in the exam, I just had to do this to explain what I was doing so that I won't just like breeze through it. So that's why I took my time to explicitly write out the steps and everything. But ideally, during your exam, you have to be fast. You have to be fast about it. Okay, so let's look for our answer here. We have what 10 raised to power what? 8. Ooh, I think there's supposed to be a minus here. There's supposed to be a minus here. So but I will pick that. And then there's this wonderful thing we have here at EdSofta so that we can serve our users better. There's this thing called report error. Okay, so actually, it actually looks like there should be a minus because there's a distance here, right? So when I see a problem with a question, right? So what I just simply do is I just report question, tell where I found what's the error in the options, and then I'm like, okay, so option C is missing a minus. And then when you send it, and it sends, and then we see it on our end and we correct it, and we are good to go. So let's move forward. Okay, now look at this. A resistance R is connected across the terminal of an electric cell of internal resistance 2 ohms, and the voltage was reduced to 3/5 of its nominal value. The value of R is, okay, so now this is actually pretty simple. So what we do here is this. So remember, I told you that the formula for the EMF, yeah, E equals to what? I bracket big R plus what? Plus small r. Okay. So the thing is this. Sorry, we have to shuffle. I have to shuffle between the board and this guy. Okay, so let me just clear off this whole thing. I think we are done with it. Okay, so now remember I told you earlier that I gave this formula is equals to, right? Okay, so now the question says initially, right, they gave us the internal resistance to be what? Let me just quickly confirm that. The internal resistance to be 2 ohms, okay? It was initially, it was internal resistance to be 2 ohms, yeah. Okay, so now we don't know what the final, the external resistance is. Okay, so now plugging, so if I just plug what I have into this, what I have is E is equals to what? My current, which I don't know yet, is equals to my big resistance plus what? 2. Okay, now it says the EMF, yeah, was reduced by 3/5. Okay, the EMF was reduced by 3/5. So now, if you reduce, so now what am I doing? So you now do what? 3/5 of what? Of the EMF. So now we have reduced the EMF by what? We have reduced the EMF by 3/5 of its nominal value. So what that gives me is this. So if I multiply this whole thing by 3/5, what I have is, so let me just call this one E0, and then my E1, so my E1 is actually equal to 3/5 of what? E0. So my E1 is now what? 3/5 of my current times what? R plus what? 2. Okay, so now if I compare my what? E0 and my what? My E1, okay, if I compare the both of them together, then the current does not change. So I just simply what? Cancel out what? My current. So I just simply cancel out what? Right. So I have what? So looking at this, comparing the two of them, I just simply cancel out my what? My current. Okay. So what I'm left is what? 3/5 brackets R plus what? 2. Okay. So if I open the brackets, what I have is, if I open the bracket, what I have is what? 3/5R, yeah, plus that gives me what? 6/5 small r. So now what are we looking for exactly? We are looking for the sorry, I want to confirm the question. Okay. Yeah, sorry for the, I don't know, breaking transmission. I don't really know what happened. But okay, so yeah. Well, so now the last question, something was wrong with it. So that's why I didn't even know that I was even talking to myself, or something was wrong with the question. So that's why I just decided to what, skip that question. But moving on, moving on. So let's just pick up another question. Sorry. Okay. So now, okay. So now look at this. It says in the diagram below, the ratio of the electric power dissipated in the 6 ohm and 3 ohm respectively is. So this is actually not really very stressful. So what you just simply do is this. So now remember, for parallel, right? Voltage remains what's the same. It's current. Current is guide that varies. So that means you can use the same voltage and then calculate power. So if I switch back to my my board, yeah, so we can just quickly go through it. So yeah, so it's pretty simple. So remember, the formula for power is what? P equals to what? IV, but you can also have it as what? I squared R. You can also have it as what? V squared over what? Over R. Okay, so if I do power, and what we already have what? We have our voltage as 12. Then we have varying resistance. So they want us to calculate the power ratio between the two resistors. So R1, I'm just going to try R1 and R2. So let me just confirm the values of R1 and R2. So the values of R1 is 3, 6, and R2 is 3. Okay, 6 and 3. So this one is 6, and this one is what? 3. So this is volts, this is ohms, this is ohms also. Okay, so we're going to use this formula because so we have velocity, we have the resistance. So just quickly plug in the formula. So power in the 6 ohm, power across the 6 ohm will just be simply V squared is what? 12 squared. So let me write that again. 12 squared over 6. So that's what? 144 over 6. 6 and 14 would be 2 remainder 2, and in 24 would be what? 20 would be 4. So it has 24 watts. Then power in the second resistor would be what? 12 squared. Would be what? 12 squared all over 3, which is 144 over 3. 3 14 would be 4 remainder 2. If I'm not mistaken, then 24, 8. That's 48 watts. Now the ratio between the two of them, 24 ratio 48. I think this is just simply 24 here 1, 24 here 2. So 1 ratio 2 is our answer. So just simply go there. 1 ratio 2 will just simply be the answer. So 1 ratio 2 will be my answer. Okay, so now the maximum power transfer occurs in a cell when the external resistance is, so now there are two options. So it's twice the internal resistance of the cell, the same as the internal resistance of the cell, is greater than the internal resistance of the cell, and it is or less than the internal resistance of the cell. So maximum power actually would occur when the resistance, so yeah, so let me just check the slide, see what, so that we can, so I can make reference to, so we can make reference to, let me see if we have it in the slide. Okay, sorry, just checking. Okay, so did we mention it in the slide? Okay, no, we did not mention it in the slide. We did not mention it in the slide. Okay, so let me just mention it. So actually, maximum power transfer occurs in a cell when the external resistance is the same as what? The internal resistance of the cell. When they are the same, then you achieved maximum power transfer. So when the internal resistance, when the external resistance is the same as what? The internal resistance. Okay, so that goes. Now a cell can supply current of this and this through a 4 ohm resistor and a 10 ohm resistor, respectively. Calculate what the internal resistance of the cell. Okay, so I think this will be the last question we would take before we call it a day, because our time is what our time is fast spent. So let me just shuffle back to my board. Let me shuffle back to my board. Okay. Sorry for the okay, so let me just clear the screen right now. Let's clear the screen right now. Okay. Oops, sorry. Okay, so now, so if you notice something, we're given two currents and what two various forms of resistance, and now we're told to calculate what the internal resistance of the circuit. We're told to calculate what the internal resistance of the cell. Internal resistance of the cell. So pretty straightforward. So first of all, remember we have a formula called calculates EMF, which is equal to what? Current big R plus what? Small r. Okay. Big R plus small r. Okay, so having said that, so now since we have what two currents and two external resistors, so we're just going to have what E1 and what E2 and substitute the formulas here. And mind you, they must be the same, because if they have the same resistance, that means they must amount to the same. If they have the same internal resistance, then they must amount to the same value here. So for the first guy, we have current of 0.4 through a 4 ohm resistor. So we have 0. Just to confirm, 0.4 through 4.0. So 0.4. So sorry. So here my current is 0.4. My resistance is what? 4. So but I don't know my small resistor. And then in this place, my current is 0.2. 0.2, and my resistance is 12. If I'm not mistaken, 10. Okay, resistance is 10, and we still don't know our internal resistance. Okay, so using the formulas, just substitute the values there. So 0.4 bracket big R is what? 4 plus small r, which is what we don't know. Then what? E2 is equal to what? 0.2 times 10 plus r, which you don't know. Okay, now mind you, these two must be the same. Okay, so having said that, so what I'm going to have is this is what I'm going to have. This is what I'm going to have. So this will be R. Okay, so if I open the bracket here, 0.4 times 4 is as 1.6 plus 0.4R, which is equals to 0.2 times 10 will be what? 2 plus 0.2R. Collect like them, so I'm going to put all the R's on the left hand side. Minus 0.2R equals to what? 2 minus 1.6. 2 minus 1.6. 0.4R minus 0.2R gives me what? 0.2R. And 2 minus 1.6 gives me what? 0.4. So if I divide both sides by 2, on the right both sides by 0.2. So what I end up having is what? 2. So my internal resistance here is 2. Okay, so we have come to the end of this section for electricity. Okay, so yeah, so I think the next thing we'll be talking on would be projectiles. So we're just going to go on a 10-15 minutes break, and then when we are back, we'll talk on projectiles. So thank you very much for joining us.